and thank you for joining us at today's webinar for Panel 10, titled Net Zero Buildings, Revolutionize and Decarbonize. We will discuss net zero in terms of decarbonization at all levels, the building, individual technology, and the grid perspective. My name is Smita Gupta, and I'll be a moderator today. I'm a senior product manager at Itron in the Distributed Energy Management Group and have worked in the energy industry for over 20 years. I'm joined by my co-lead for the panel, David Villetta from Slipstream, who will be moderating the Q&A and the discussion at the end of the session. Before we begin, a few housekeeping announcements, which I guess you've heard in other sessions too. First thing, your screen is customizable. So as you're logged into the browser, feel free to make various windows large or small. You'll see the menu bar at the bottom of your screen. Click through the widgets at the bottom to be sure that you're not missing on any options there, especially the screen that you're viewing now and the Q&A button there. Presentations can be downloaded as PDFs from the presentation list in the menu. Attendees are in listen-only mode, but can submit the questions through the Q&A box. And we'd encourage you to do that throughout the webcast, because our format will be, we'll go through all the presenters first and then field the questions at the end. So please be sure to type the name of the presenter with your questions so that we can address it appropriately. All presentations will be available for on-demand viewing within a few days on the Engagement Hub. Later this afternoon, after the panel sessions, informal sessions and social times will be offered through Zoom links. To access these sessions, you'll find the links in the session icon on the menu bar. On behalf of ACEEE, we wish to first recognize and thank our sponsors for this event. E for the Future, Energize Connecticut, Eversource, National Grid, Sacramento Municipal Utility District, SMUD, Southern California Gas, UI as gold sponsors, ComEd, the Energy Coalition, Energy Trust of Oregon, Johnson Controls, NEA, Samsung, TRC as silver, Guidehouse, New York Power Authority, Opinion Dynamics, VEIC as bronze. And now I'd like to introduce you to our panel of speakers. We have 3 speakers in the session today. Paul Torsellini, Principal Engineer for Commercial Buildings Research at National Renewable Energy Lab, NREL. Bing Liu, Senior Manager at Northwest Energy Efficiency Alliance, and Ellen Franconi, Senior Research Engineer at Pacific Northwest National Laboratory. We'll start first, as I said, that we'll go through all the presentations, and we'll start with our first speakers, who doesn't need much introduction to those of us who've been in the industry over 2 decades now. Paul Torsellini is a Principal Engineer for Commercial Buildings Research at NREL, and he's also on the faculty at Eastern Connecticut State University. Paul is a key contributor in the development of the Advanced Energy Design Guides for ASHRAE, AIA, IES, USGBC, including chairing the technical committees that produce the Zero Energy Design Guides. Paul is a registered professional engineer holding a PhD from Purdue University, as well as an ASHRAE Fellow and Distinguished Lecturer. Paul has authored and co-authored more than 50 papers and articles related to energy efficiency and zero energy buildings. With that, I hand it over to you, Paul.
Okay, thanks, Smita. And I do want to make sure I recognize Smita and David for leading this panel. It's a lot of work to gather all the papers and ride herd on everybody to get them done and get all the reviewers and responses. It's just a heroic effort to put one of these panels together. And so I want to make sure I recognize the 2 of them for their time. As Smita said, I have worked around zero energy buildings for a long time. And kind of starting the discussion, we had a paper 10 years ago that was really a framework for zero at the time. And a lot of questions have come up, technologies have changed, and really this paper was a genesis of talking to lots of people and our team internal to the lab that thinks about this. So I do want to recognize the co-authors who have put a lot of brain cells into the thinking behind this paper, Sammy, Shanti, Bill, and Ben. And so just as a little background, buildings are using 40% of the US energy, 70% of the electricity generated goes to buildings. And that 70% of the electricity becomes really key as we get talk more about this. And some of it is there's a lot more interest today in all electric buildings and shifting to all electric buildings. But as we look at energy efficiency, the growth of buildings, we're still building buildings, and that growth is close to the energy saved. And so on the screen now is a graph from EIA that shows the kind of the trend in how energy consumption is changing. And yes, it's leveled off. It went down for a couple of years, and now the rolling average, it's hard to tell, but maybe it's going up a little bit. Certainly, I think with the events of the last year, we'll probably see a decrease, especially on the commercial side, going into next year. But whether you want to decide if it's going up or down, the point is it's still a lot of energy, and that it's not a strong downward signal. So we're building buildings at about the same rate that we're saving that energy. Likewise, another thing that has changed pretty dramatically is the cost of photovoltaics as installed values. And so on the screen here are different costs for residential and commercial utility scale PV. And you can see a pretty dramatic decrease, something about 25, 30% of the cost today compared with 10 years ago. And that is really changing the landscape around the renewable resources available to buildings. When I started thinking about this, 25 or so years ago, the notion of putting renewables on a building was cost prohibitive. A few people did it, especially if you were grid independent, but really you couldn't afford to do it. And today it is readily available, and that market is increasing pretty dramatically. And so, this kind of hockey stick curve showing that growth, especially on the utility scale, but the growth is pretty good on the residential and commercial scales as well. And so a couple of other just things to think about in terms of how buildings and the grid kind of interrelate to each other is that the utility grid has been around for a long time, not quite as long as buildings, but certainly has been designed around meeting the loads of those buildings. So again, 70% of the electricity today is going into buildings from that first slide. And yet that capacity factor of the grid is decreasing. So there's less alignment between the load and existing generation compared with when we actually need that building. And so we're seeing that especially in the late afternoons. And I'm sure there's other sessions that are talking about the grid shape and how it's responding. But if you end up with a late afternoon grid peak, you're looking to how do you meet that? And a lot of times it's been with some kind of gas turbine or gas technology to meet that afternoon peak, or we need to really think about some mass amounts of storage to meet that. So kind of backing up a little bit here, when we talk about energy and we measure energy, energy is one of the few things that we can readily measure at the building boundary, but it's long been a surrogate for environmental impact. And that environmental impact and what the focus has been has shifted a little bit with time. Certainly initially it was a lot about water and air quality, mercury, sulfur, nuclear waste, habitat destruction. More recently, a lot of discussion around carbon emissions. And all these things get tied back to energy because that's really the only thing we can measure as it's crossing the boundary. A lot of times I wish I had this meter that I could put in front of a building and kind of dial in the metric I wanted, some kind of sustainability meter, and have it just respond. But at the end of the day, we're measuring energy as it's crossing the boundary. And then we use conversion factors of some sort to shift those other metrics of interest. And so kind of the overall premise is, been over long periods of time that if we consume less energy, then there is less impact on all of these metrics. So, really the objective here is that how do we reduce that impact? And so that fundamentally is the concept of, and I stuck a couple of different nets in here. If you want to have an entire informal session, we could probably have an entire informal session just on where does the word net go or does it go? But the concept of zero net energy buildings is really about balancing consumption with that production. And if we have less consumption, that really means that we can make that balance easier with less production. And so when we, early on in the days of this, when we were talking about zero energy buildings, we did a feasibility study and looked at a 50% energy savings and 50% roof coverage, and there was enough roof area to power all the commercial buildings at this level. We've also looked at numbers of examples, especially of these earlier generation zero energy buildings, where we were looking at data and looking at what that balance looked like, and even realizations that, solar is not generated for large periods of the day. And in reality, to get to zero, even on a cloudy day, there's probably some time during the day where you have to export that energy back to the grid. And the grid has, for a long time, been a pretty effective mechanism for taking that energy and redistributing it. And so I mentioned we had an original framework, which we've dubbed in this paper as version 1.0. And really, it was a method for determining what zero was and some of those boundaries. We could talk about the building itself. We could talk about the site. We could talk about a district or a group of buildings, maybe a city block. Campuses became popular kind of boundary points, and even portfolios. So if I own a number of, say, retail stores, I can put all those together and talk about those as a group. We can also talk about metrics, and that might be site energy or source energy, energy cost, emissions. And again, after site energy, a lot of these other things end up being some kind of scaling factor. We also looked at some kind of classification based on the sourcing of those renewables in that original paper, and the ability to determine if a building was zero in somewhat an easy sense because we had utility bills. And one of the important things that we've heard over time is that people want to know if they've achieved that end result and want to have some control on how to measure that. But there are clearly some things that have been missing here, and some of that was alignment with renewable resources, and that there is some ability to use storage, realizing that storage, especially at the building level, is somewhat of an energy loser from the pure metric of measuring energy at the site, because the round trip efficiency is not perfect for most storage. But there's also now this advent of exporting to electric vehicles. And I should probably say not only exporting, but potentially importing from those electric vehicles. And that with the large amount of off-site renewables, we need to think about how that has value back to buildings, as well as the on-site renewables. And so one of the things that we kind of established on this paper is, what is the ultimate end goal here? And we basically said here that 100% renewables, if I can get to 100% renewables 100% of the time, does that really represent where we ultimately want to be? And so in order to do that, energy efficiency has a very central role in making that happen. Has a very high value to the utility grid, has a high value to building owners, can be deployed 24/7 in a lot of cases. And so that is an important piece of continuing our discussion about zero energy buildings. And then also this continued ability to evaluate a building with simple data. So we might want to talk about minimizing the impact of externalities in the metrics. So there's kind of two pieces there. One is, what does that evaluation look like? And can I still evaluate the building easily? And then can I minimize the impact of externalities on those metrics? The design strategies can have a very large impact if the building is based on metrics and it's out of the control of the building designer. So, if you design a building and you realize that your dependency on being zero or not is completely external to the building, you might not be incentivized to carry on good design and maintain that level of efficiency. So as we talked about the concept development here, really looking at energy flows as they cross the boundary. Interestingly, not all energy flows get measured at the end of the day. They can be time dependent. And in reality, we're probably only measuring energy flows that are hooked up to some kind of utility infrastructure, and not every energy flow. And so then the point of purchase is still an easy boundary point and a kind of a central focus on what we're going to measure and when we're going to measure it. And from that, all other metrics are calculated. And so, looking at the boundaries, that point of metering, there's a clear building or a portion of the building. You might be looking at, say, a store in a shopping center, which is a portion of a building, communities of buildings. You may even look at it as a larger sense, towns, cities, states, maybe even utility balancing regions, continuing with the portfolios, but also maintaining some span and control of a project that we want owners and design teams to really, be one of the key points of engagement for being responsible for how buildings function and operate and their role at reducing our energy and environmental impacts. And it's interesting, whether we're talking about a single building or lots of buildings put together, developing metrics that work for single buildings, but they should also work for these larger boundaries, these multiple sets of buildings. And so I've mentioned the energy flows. This is a graphic right out of the paper that just try to quantify some of the directionality and the flows of that. Notice that the on-site renewables is really part of the building or inside that boundary, as well as the storage elements that are there. And that these energy flows, one of the things that is changing is the time valuation of when that energy is used. And so you can end up with a multiplier that's a function of time and not just kind of aggregating up those energy flows. So looking at a couple of metrics related to this that I think help frame and think about some of this alignment and maintaining some of the efficiency goals. One was something we've dubbed as the solar use index, which is really a measurement of the percentage of solar energy that is used in the building when it's available. So often buildings are, during the day, have solar panels on the roof. They can export that energy and then they use it, can purchase it back at some other time. And, one of the things is, am I using that energy at the time that's generated? Am I designing my building such that it can use that energy, or even that energy, that renewable energy as it's available on the grid? And so you can extend this definition to kind of grid availability of renewable energy. One of the nice things about this metric, especially if you're looking at it just inside the building, is that it's very easy to measure because a typical net meter today already does the integration for you and logs the inflows and outflows. And you can combine that with an aggregate monthly renewable energy total and actually get an integrated value for the percentage of solar energy that is used instantly in the building. The next one is a load coverage factor, and it's really a measurement of the percentage of load covered by these solar resources. Now, in order to do this one, you do need some interval meter data because it's important to know when that renewable energy is generated and how it matches up with what's being bought and sold at any moment in time. So graphically, we can look at these. These are the same load profiles. The one on the left, the blue is the load of the building, and you can see the solar kind of in the middle of the day. And in this case, 50% of the solar energy was actually used in the building, and the other 50% was sold to the grid and then purchased back probably at nighttime in this case. That compared to the, and I realize that those labels are actually backwards on this graph because the, oh, no, I'm sorry. Let me say that again. So 50% of that, of the load is, or no, I had it right the first time. The labels are backwards. The 50% of the solar energy is actually used in the building, where in the other case, only 63% is actually used in the building at that moment, or is covering the load at that moment in time. And so we can apply these metrics to actual examples. For example, you can look at a house. This was actual data from a house with a 9 kilowatt solar panel. Only 17% on an annual basis of the solar energy was actually used in the house. The other 83% was sold back to the grid and then repurchased later. And that storage, that in this case the grid is being used as a storage element, that the maximum storage on an annual basis is actually 22.5% of the annual consumption. Looking at the load coverage factor, really we can look at this load coverage factor and say that as we deploy storage in a building, we can increase the amount of load that I can cover in the building with that solar because of shifting some of that load with storage. And so you can see this analysis with several different building types. And as you know, the increase in storage actually shows that more of that load is covered. And so just wrapping this up, and there's lots of other details in the paper, that the building can really be designed to better align with the renewable resources, both on-site and off-site, striving for 100% renewables 100% of the time. And then we can look at this expanded definition, the ability to value energy as a function of time. You know, we could talk about increasing the export if the grid can use it, or reducing the loads to account for losses and non-use. So there's various ways that the current formulation looks at valuing that energy. But ultimately, if we want designers and operators to be an active market player here, they do need some long-term market signals so that they can make effective design decisions. And I know some of the kind of rules of thumb that we've talked about are things like, you know, have buildings that use more energy between, say, 10 and 2 every day, and a whole lot less energy between 4 and 8 or 9 p.m. every day. And even taking simple steps like that can go a long way in allowing for more renewable penetration, as well as enabling more energy efficiency. So again, I'd like to acknowledge the different folks and DOE for continuing to support efforts along these ways, along with the co-authors for the paper. And I will end there and turn it back over to you, Smita.
Thank you, Paul. So now, just as a reminder, we'll go through all the presentations. So please type in all your questions for Paul in the Q&A menu that you see at the bottom of your screen. And again, we request that you add the name of the presenter so that we can address the questions more appropriately at the end. And okay, so with that, we'll move on to the next presenter, Bing Liu. Bing Liu is a senior manager at NEA, leading the Codes and Standards and New Construction Department. Bing leads the development and implementation of building energy codes, appliances and equipment standards, commercial and residential above code programs. Before joining NEA, Bing was a group leader at PNNL, overseeing the Building Energy Research and Analysis Group with 30 researchers. She was also program manager of Building Energy Codes, leading PNNL's research team to support the development and implementation of building energy codes in the US. Bing is an internationally recognized technical expert with over 25 years experience in building codes and standards, large-scale building energy simulation, energy efficiency technology and analysis, building performance metering. Bing is a registered professional engineer, fellow of ASHRAE, a member of ASHRAE Standard 90.1, 189.1, and technical program chair of ASHRAE 2020 annual conference. She was the lead author of award-winning Advanced Energy Design Guide and ASHRAE Distinguished Lecturer. Bing was featured as one of top 20 women in HVAC industry for 2020 by Engineered Systems magazine. And with that, I'll hand it over to Bing.
Thank you, Smita. When I submitted my bio, I didn't realize you're going to read the whole bio, so I apologize on that. it's very interesting. I always kind of like a big fan of Paul. In terms of he always lay out what the future looks like in 10 years, even in 30 years. So when Paul's talk gave us the layout of what the zero energy and zero energy building really means, we also work really hard try to meet the goal towards the zero energy ready from cost perspective. So the topic I'm going to presenting is really one of the one I think a major breakthrough in terms of how to address HVAC system efficiency in order to help us to achieve zero buildings through the cost perspective in the next decade. I'd like to acknowledge the co-author of this paper. From here, you can see this is actually a true team effort because we have a co-author from multiple organizations. And the work we've been conducting here, it took at least 3 years hard work to get into today's point. The co-author of the papers include Neil Grisby from NIA, Superior Go and Mike Rosenberg from Pacific North National Lab, Duane Johnling from City of Seattle, and Heather Burpee from University of Washington Integrated Design Lab, in short, IDL. The topic I'd like to cover in this short press of the time will be, I'll give a little bit background and the context of the topic in terms of the system, HVAC system metric, and the methodology, and how we got this new concept adopted in the Washington codes, and also gave the highlight of the pilot project we have conducted after this proposal was adopted into the codes. I'd like to share some of our suggestions and experience how to use the same metrics to develop the utility incentive programs, and also how these metrics can be used to state and cities directly to address the climate action plan and contribute to the carbon reduction goals. And I will share the wrap up the presentations with a few takeaways as a part of the conclusion. So we create a new algorithm. I guess it's called the Total System Performance Ratio, in short, TSPR. What is a Total System Performance Ratio? It's actually very simple metric. What is you calculate what's a total annual building heating and cooling loads, and you divide by the carbon emission generated of the HVAC system in order to provide the heating, cooling, ventilation to the building. And I will talk a little bit more later on. The matrix is quite flexible using the same methodology. You can use a carbon as the emission as your matrix. You also can use the site energy, source energy, or energy cost. So I will talk a little bit more about that. So why we created this metric? The primary goal is really try to encourage low emission, low energy use HVAC systems in Washington State, and that's really aligned with Washington State policy goal for zero energy homes and the commercial buildings by the year 2020-30, and also a carbon reduction goal as well. So we have introduced this codes requirement. Now is fully adopted in the new Washington commercial codes. The new codes are going to be effective in February next year. That means for all the commercial buildings, in order to get a permit from beginning of the next years, you have to comply with these new codes. What I show graphically is this the TSPR concept is more similar. If you look at it from the HVAC equipment point of view, it's more similar to system efficiency ratio rather than ER, which is you take into account the power load performance, as a whole building, not just as the design capacity of efficiency. That's what we try to measure. The question is, why we need a new metric, and what problem we try to address. In the current code structure, we have treated all HVAC systems as the same. As a show of the graphic developed by one of the co-authors, Duan Jianlin, is all, and also quote his words, that all HVAC system can be a big dog because it is compared only to others of the same breed. What I mean in the code world, it means, code has a prescribed requirement on the component of HVAC system, and based on the system selected by the designer engineers, and the codes have a specific requirement of equipment efficiencies or control requirement, and etc. And there's no penalty for using lousy HVAC systems, but there's no reward for using great system type. So at the end of the day, there's no motivation in industry to improve system performance or really think holistically. So I want to illustrate, when I'm talking about what's the code structures, on the right side of the graphics, when we show, the code, currently the code structure is really focused on the component level. We also call that prescribed path, depends on what kind of the building component you have and set up, minimum efficiency required for you to meet. So the component level of the complex path or prescribed path it's mostly common used complex path for buildings because it's easy to use and it's more simplified to compliance as well. But the limitation is it doesn't credit the selection of more efficient system configurations. And it results in selection of the system solely based on the lowest construction cost or the local construction norms. And the resulting the building system, well, fully compliant codes could be highly inefficient. On the other side, on the left side, codes does have a whole building modeling performance path where this whole building path, compliance path, provide great flexibility where the designers can trade the improvement of performance of some element for substandard performance of others. The challenge of this is less commonly used compliance path compared to prescribed path, mainly because it's relatively more costly to conduct a whole building identity modeling for this path, and also it's time consuming. So it's a lot of times we see this whole building path used for the large and complex building. And so there's no in-between between the component level and the whole building level. And the total system performance ratio metrics that provide a solution for HVAC systems which incorporate the simplicity and the ease of the use of their prescribed path, as well as provide the flexibility of the performance path. When we get into the code language, its TSPR requirement in codes is quite simple. So what I have here is what's the code requirement. For office, at least currently in Washington codes, they only apply to the 4 building type for office, retail, library, and the schools. Your designed system, the TSPR value should be greater than or equal to your TSPR of your standard reference design. And the standard reference design, also we call that as a baseline design. And there are also exceptions, 9 exceptions laid out in the codes. That's mainly for the smaller size of the space. If you have less than 5,000 square foot, you don't need to require to comply with TSPR. Or if you have less commonly used HVAC systems, such as using district heating water, chill water, you have exceptions as well. There's some others as well. It's laid out in the codes. Want to give a quick snapshot, how the baseline system design has been defined in Washington State. For the modeling graphic I'm showing is representing the small office, library, retail, large office, and the school. Again, this is the 4 building type are regulated to need to have a TSPR calculation. The whole process was pretty long, and because it's a very hard to define a single set of baseline representing of that building type. Our starting point was really using Northwest Regional Commercial Building Stock Assessment. That gave us the base in terms of what has been the commonly used HVAC system type in Washington State, with the statistically valid kind of the survey data from our stock assessment. We also convened, in addition to the authors, convinced the code stakeholder groups, and including the designers, engineers, energy modelers, and the code officials. I would say debate to that through the whole code adoption process. It's 2 years process to determine very details what's the baseline systems. And the baseline system have to meet other prescribed codes requirement of the new commercial codes as well. It's pretty already stringent as a baseline system because back to the 2015 Washington codes, for the prescribed paths, you needed to have dedicated outside systems in your HVAC, which is really separating the treatment of outdoor air from the space heating and cooling loads, and with combination with energy ventilation recovery, ERV. I realized in the slides, the detailed specs, it looks very small. It's also on our paper. And also you can find the detailed baseline system specifications in the new codes book as well as a part of that appendix. I'm not going to go to the detail on that, but the other information is available. Another major change from this metric development, as I mentioned earlier, is what you try to calculate in terms of HVAC system efficiency. You can have a multiple way to calculate it. You can do set energy, source energy, energy cost, and the carbon emission. In order to closely align the Washington State policy goal in terms of carbon reduction, the Washington State Board decided, and with the recommendation from Department of the Commerce in Washington State, to use a carbon emission as part of the calculation of TSPR. What I have done here is showing the carbon convention factors we've been used, and that's the also development generated through the whole codes consensus and public engagement process, with quite a debate and a balance among the utilities and the stakeholders. So that's at least the convention factor has been used as a base to develop the codes in Washington State. Because in order to calculate your building loads and the energy and the carbon generate from HVAC system, consumed from HVAC system on these loads, you really need to do the whole building calculation. So we recognize how important to provide convenient and free software tool to provide this kind of the compliance tools to help the market not to accept it and also comply with that. So what I have shown here is the tool P&L has developed using DOE's Building Energy Asset Score as a platform. And the asset score is a simplified tool for assessing the building energy efficiency. It's a pretty clever and very easy to use. The tool itself has a very simplified way to enter the geometry and the quick, intuitive click through for you to just describe what's your proposed HVAC systems, and the tool will automatically generate the baseline TSPR and provide the output and the report to the user. I provide a link here. Everyone is free to use, and we also provide their technical support and the trainings along with this compliance tool. This one is really just showing, because this requirement, P&L did quite extensive studies just looking into for commonly used, such as we just use a large office as example, for commonly used systems, what kind of systems can pass the TSPR requirement and what cannot. I don't know if you can see my cursor. So the first one is the baseline requirement. And the second group is the fan coil systems. And the third group is the VV with hot water reheat. And the last one is the VV with electrical reheat. And the red bar is if you have the system you pick, but you just use a variable minimum efficiency requirement, you're not going to pass the TSPR requirement. But if you use a higher efficiency levels and better controls, you can pass the TSPR. So if you have a fan coil system VVs, you still can pass the TSPR, but you really need to pay attention of your system designs so to achieve the better system efficiency. We understand, since this is a novel idea and first of the kind in the coast world, we needed to really think through how to prepare the market for this new requirement. So the UW IDL and the NIA has been working on this last part of the last year to develop the pilot project to testing the TSPR. And right after TSPR adopted and before it's effective. So this is kind of sweet time for us to really prepare the market on that. The objective of this pilot was really to collect the feedback from design professionals on the usability of the TSPR tool and through the real world project, and also including their experience in terms of receiving the trainings and the implementations, and also the report. So the design of the pilot, so including the really three main elements, including the outreach and the engagement to the design communities, and training, testing, evaluation, and the feedback. So what we have is a broader range of we were able to recruit 12 real-world projects, covered different building types, different size of building, and the focus is really on the smaller size of building for major renovations, new construction, and also testers representing from large consulting company, design build companies, small services, and also their HVAC services with their different climate and geographic areas in Washington state. The main takeaway from the pilot project was, it is promising if we move the project close to carbon reduction goal and save the natural resources. The tool itself is easy to use. Its reporting is take no more than 2 to 10 hours to finish the whole project. So compared to whole building simulations, is it's about 10% of the time. And it's a very valuable cost compliance tools. And we also receiving a lot of construction feedback in terms of how to improve the future trainings and also how to improve the output report, particularly if the project not passing the TSPRs, what kind of suggestions the tool can provide to help the designers to rethink their system design. So after that, P&L and IDL has developed a lot of customer training. I'm not going to talk about all the detailed training. It's just in the past summers, we have offered to 500 professionals have signed up on just 2 sessions of the training. So it's quite popular to receive that. And I want to share a little bit about further how the tools help in terms of bridging the gap for the utilities. If you're familiar with utility incentive programs, we commonly see 2 types of incentives. One is a measure level of the incentive, which is, it's a relative straightforward, normally used to simple buildings, but with the limitations where as a, wages basis of the incentives, there's a lot of limitations. And with the costs continue to increase the stringency, there's a headroom to provide this kind of incentive as the measure-based level getting less and less in terms of cost effectiveness from utility perspective. And there's a customer project normally used for large building and can achieve the deeper saving with a lot of flexible, but it's a pretty costly for utility to operate that and for their customer to use that as well. So TSPR is really bring a gap in a way is, again, this is a very simple matrix. So utilities, the codes can set up at 100% TSPR level. Utility can dial that up to 10% more, 20% more, even 50% more as a utility incentives. And also because the goal is really setting up by their carbon, it directly can track the contribution in terms of carbon, such as City of Seattle has considering adopt the more aggressive TSPRs at Seattle, the new Seattle commercial codes. And also you can expand from the 4 building types in Washington codes to others building types, such as in Seattle, they has expanded to the multifamilies. So in conclusion, the TSPR is really reward integrated and efficient system design, and the free calculation tools offered can help to streamline the between the cost compliance and the utility incentives, and it's really reduced the utilities overhead operator program if they offer this kind of the measures. And the two, because well-established methodologies, the TSPR metric can easily tailored to your jurisdictions. Again, you can pick your own baseline system, you can pick different metrics, and can really easily apply to Beyond Codes program. Given that, I will turn that back to Smita.
All right, thank you, Bing. We'll move on to our third presenter for the day. And as you've seen, we've evolved in this session from starting out with the building level, then the technology level, and all in the vein of net zero. We're no longer limiting, as you see, to energy, but it's more about grid interaction and decarbonization. So keeping with that theme, our next presenter, Ellen Franconi, is going to talk about the grid interactive aspect of buildings. Ellen Franconi is a building systems engineering, is a senior research engineer at Pacific Northwest National Lab. Ellen supports DOE's efforts to advance model building energy codes as part of her work within PNNL's Buildings and Connected Systems program. Her research informs the consideration of grid interactive, net zero, and resilient buildings in model energy codes. With that, I'll hand it over to you, Ellen.
Great, thanks, Smita. Yeah, hello, everybody. I'll be talking about some research I've done with my PNNL colleagues in support of DOE's Building Energy Codes program and their efforts to advance national model energy codes. And specifically, it focuses on how can codes, energy codes, model energy codes, support the adoption of grid interactive buildings at scale. So I'll start out by providing some context to explain the connection between GEB, the grid, and building energy codes. Then I'll introduce our research and provide some of our results and finish with a summary discussion. So this California duck curve, I'm sure many of you have seen it, but it provides a good visual for us to understand the importance of GEB to the grid. So what this shows, it's the net load after renewables on the California grid. It's for a typical day in the last week of March. And you can see the net load shape on the grid from 2012 down to 2020. And you can see initially, you know, there's not much of a curve on that duck. But as the renewable energy policies have had more success, more impact, you see that curve getting deeper and deeper. And as a result, the ramp down periods when PV is coming online is getting more steep. And particularly the ramp up is very steep. And it's during these steep ramp periods that create management problems for grid operators and challenges for grid stability and resilience. So you can see that GEB is becoming more needed and greater value to the GIB. So in return, GEB in buildings becomes more important and more important to energy codes. And because buildings consume 70% of US electricity use, they really do have a big role to play. So what is a grid interactive efficient buildings, or GEB? You can see in this diagram some important attributes of a GEB. In this graphic, I should mention, is from research being done by DOE BTO and their GEB initiative, and they do have a lot of very informative reports if you want to follow up on this topic. But basically what it shows is it shows different demand flexibility technologies. These can be directly connected to the grid, such as connected lighting, smart thermostats, connected HVAC systems, or it could be that the building energy management system, the BAS, building automation system, is connected to the grid. And in turn, that can then connect different building systems and optimize their operation in relation to other systems and on-site renewable energy systems and batteries and energy storage. And on the right, it shows, excuse me, 4 attributes of buildings that are helpful or important for them to be considered GEB. Energy efficient. Overall, it's going to reduce energy use and peak demand. That they're flexible. They can make the most of on-site renewable energies and respond to a grid signal being connected. They have a two-way connection and can respond to that grid signal and also to occupant needs. And they're smart, so they make the most of all this data, the controls, the sensing within the building to co-optimize operation in terms of costs, energy use, and comfort. So one challenge about considering GEB in codes is valuing it. Specifically, historically, in code development, when you're trying to introduce a new code change proposal, such as a new requirement for efficiency measure that needs to demonstrate some sort of cost effectiveness, what that analysis is based on is a flat electricity energy rate in terms of $1 per kWh cost. That includes energy and demand. But if you try to do any sort of load shifting or flexibility, it won't demonstrate savings unless it's impacting that flat rate. So obviously, this is an overall challenge, and we need to do a better job of understanding how rates do change and at what rate they change. And as shown in this graphic, this is also out of the DOE BTO reports. This is specifically for lighting, but it shows how energy efficiency measures can affect efficiency, but they can also have demand flexibility aspects or be targeted directly at demand flexibility in terms of shedding and shifting load. And if they can react at a very fast time scale, they also can do what's called load modulation, which can mostly affect power quality. But you see, besides just considering a flat energy cost reduction, there is much more value that these demand flexibility measures can offer to the building owner and to the grid. So as part of our work in building energy codes and understanding the existing code development process, we wanted to get a better sense for how prevalent are time of use rates in the US and how important is considering them. So we drew on some research. This map was created by NREL, and it utilized data contained within the OpenEI database, which is a US utility rate database. And this includes, I think, about 6,000 rates across all utilities, across all countries in the US. And you can see that many of them have demand charges. And so if we aren't considering demand charges, well then we aren't really fully valuing all the different types of efficiency and demand flexibility measures that we could be. Oops. So what we did was we drew on our building code or model code prototype buildings, which actually I think have root in previous work that Paul has done with the DOE prototype buildings. But these prototypes have veered off. They're a little bit different. They actually include all requirements affecting energy that are specified in code. So they're maintained and they're very detailed. But specifically, we use the model office building prototype. You can see its general characteristics from the picture here. And it has packaged AC rooftop units, a gas furnace with VAV boxes and reheat. We evaluated its performance in 3 different climate zones. Those different numbers represent Tampa, New York City, and Rochester, Minnesota, respectively. And we also looked at different rates. We looked at the average blended rate, which is what historically has been used in code development. We also, using that OpenEI data underlying the NREL map to create a representative US time of use rate. And in addition, we used an actual rate. It's the Con Ed New York City time of use rate to characterize a more, I'd say, aggressive rate. And then we looked at different energy efficiency and demand flexibility measures to understand like how important is that and what can we learn from analyzing it. So this is a little bit more detail on the rates that we used. I'll walk you through it a little bit. It's a winter week and a summer week. And you can see on the left axis, it's the cost per kWh, the energy charge. On the right, it's demand charge. And we showed the 3 different rate structures that we used. The ASHRAE blended rate, that's just this flat gray line across both seasons. Then we have this ASHRAE, what we're calling the ASHRAE time of use rate, the representative US rate, and that's in green. So they do have a time of use energy charge shown with the green. There's also a base kW rate in the winter. It's a dashed green line just below that solid green line. And if we look in summer, for that rate, you see there is additional energy charge that varies over time of day, and a base demand charge that's flat, and also a peak demand charge shown by the dashed line in green. And then to look at the Con Ed rate, which represents, again, a more aggressive rate, you can see these solid brown lines being very low. So the kWh charge is very little, but the kWh charge is quite significant. There's a base charge and a very extreme peak charge as well in winter, and even higher in summer. So in addition to those 3 different rates, we looked at a variety of efficiency measures. We classified them in 3 categories. One is standard efficiency, and this included looking at window solar heat gain coefficient, improving it, decreasing it, and also improving the AC unit cooling efficiency. In terms of demand flexibility, a lot of these were load shedding or load shifting measures with controls. Since we were using time of use rates, we knew when the time of use rate period could be, so these could effectively be pre-programmed within the building automation system. So we had a lighting load shed during the peak demand period. That's demand. So in summertime, based on that ASHRAE time of use rate, we also had some, pre-cooling, preheating, and a little additional outside air ventilation rate in non-peak times to carry us through the peak times. And we did evaluate one distributed energy resource measure, which would be on-site battery storage. Okay. So one thing I want to point out, because normally, maybe in your work too, when we're doing performance analysis, we look at annual energy savings and cost savings. But when you start to look at demand flexibility and GEB, you really have to do a much more granular analysis. And so this graph shows the peak day in September and the different load shapes for the baseline building and then the building with each of these different measures and how it impacts the load shape across the day. And so they're in the three different climate zones as well. So the red dashed line is the baseline. And we don't really have a lot of resolution here to see the difference between the different measures. But one thing to note is, and also the shaded line is where the ASHRAE time of use rate is where the summer peak period is, where their peak KW period happens. So our measures were attempting to move the peak out of that period. One, it's hard to do that when you're trying to characterize a measure. Historically, we'd characterize it, we'd apply it across climate zones, we'd apply it, to different building types even. But you really have to take a much more customized analysis and see what's happening at the load shape level. And also, we saw in one of these measures, this blue one, the setup cooling with pre-cooling. We really peaked out beforehand in trying to avoid a peak in the peak demand period, and this didn't always show good results. So I just wanted to point that out. Another result that's pretty prevalent when you start looking at the data is the difference the rate makes. So we have the flat rate. This is the annual energy costs and the breakdown between KWH and KW charges, KWH being in blue. Flat rate, of course, is all KWH. The representative time of use rate is very similar in annual energy costs, but the breakdown is different. And once we get to the Con Ed rate, the aggressive time of use rate, we can see it's all about demand. And so certainly with the more aggressiveness or the higher the demand charge, it can really make a difference in a customer's motivation to flex their loads and install these types of measures. So as part of our analysis, we also did a cost effectiveness calculation. So here's some data that underlie that analysis. So it includes the first costs, O&M costs, and the measure life across the different measures. So it was interesting for me to see when in putting together these numbers was that not only did our measures kind of fall into different categories based on being more standard efficiency or demand flexibility, excuse me, or being a distributed energy resource, was their cost. So the ones we chose for demand flexibility, it was more about controls and a controls reprogramming. So those were really low cost, nearly no cost. The energy efficiency measures were more expensive. And of course, the DER, the battery, was very expensive. Although we did look at 2025 prices because prices are coming down so quickly, just to forward on that. Okay, so here are the results. There are a lot of them, but and you can refer to the paper to look at them more in more detail and follow the discussion. But there's just a few things I wanted to point out about this. So here you see we have our 3 climate zones, we have the measures in the baseline building, and then we have different columns which show corresponding values for the 3 different rates we looked at, including the blended rate, the time of use
Hi, Ellen, we can't hear you. Ellen, we can't hear you at all at this point. And I know you still have perhaps one more slide to get through. At this point, perhaps I'm going to request that David, I think we should step into the Q&A. Sorry to not have the finality of Ellen's presentation here, but she had one more slide to go over. And if her audio comes back, we can come back to wrap that up. David, do you want to take it on from here?
Sounds good. All right. Well, thanks, Ellen, Paul, and Bing. You all provided an excellent representation of panel 10. Before we jump into the questions, please keep in mind there is an informal session on zero energy buildings later today at 4:30 p.m. Eastern, where I'm sure a lot of these topics will be discussed in greater detail. So we have about 10 minutes remaining. So let's jump in with some of the questions. There are a lot of questions that came in during the sessions. Any that we don't get to right now, we will follow up with you later and get those answered for you. So first, we'll start off with Paul. So Paul, 100% renewables 100% of the time. Question from Dwayne at the City of Seattle. So some buildings have high process loads, restaurants, hospitals, laundry, data center. The question is, should those buildings be required to generate all of their own energy? For example, Dwayne once calculated that a typical Burger King would need nearly an acre of PV. Do you want to take that one, Paul?
Sure. Yeah. So that is definitely a question that we've gotten often over the years. If you go back to a paper that we did in 2006 at Summer Study, it's interesting to look at least the commercial profile of buildings where you've got some highly dense buildings, and you mentioned some of them. You also end up with lots of tall buildings that also would be really challenged to produce all of their energy on the site. And so what that original analysis looked at was that there's enough commercial roof area to actually power many of these buildings. And so when you look at a whole community, so that starts to look at these larger definitions or these larger boundaries for zero energy buildings that look at all the warehousing that we have, fly, I guess we're not doing too much flying these days, but around a lot of airports, you see lots of warehousing. And those warehouses are needed to support a lot of the other commercial building stock. And when you combine all of those roof areas, there is actually tremendous potential to, at least on an energy quantity point of view, power those buildings. And we're also seeing the advent, and I showed it with some of the pricing of some large-scale solar farms, large-scale wind farms, which obviously are going to help augment that as well as making up for buildings that might be kind of legacy and not as efficient. And so a lot of this has to do with what that boundary is. And in some ways, if you have a warehouse building, and I realize it's very utility dependent, it's somewhat short-sighted to put PV on that building and only power just that building without having the ability to kind of virtually meter that to other buildings. And I know most utilities and states are not, quite positioned to do that, but from a physics point of view, you can make that happen. And then there's, kind of the time alignment of that. So there's the amount we can get to with the rooftops. The time alignment is still a much bigger challenge, and that's some of what we got into with the version 2 paper.
Great, thank you, Paul. And then moving over to Bing, so question from Liang at Lawrence Berkeley National Lab. Any plans to expand the adoption of TSPR to other states? If so, what does the roadmap look like?
That's a really good question. The work already under the way. I think across the country, in terms of codes adoptions, there's only a handful of states really have resources and the policy drivers to develop is more like its own codes, like California as example. And Washington State has been very progressive in terms of the code because the policy driver, but its adoption also a lot of times based on the national model codes, such as IECC or 90.1. So the logic start, in order to scale up and influence the other regions, in addition to Washington State, one of the key strategy is to influence and introduce this system metrics into the national model codes through actually standard 90.1 and IECC. What we have been doing is we use the Washington State codes as a test bed to collect the market feedback and address the barriers as much as possible. And then so you can see the challenge is expand the building types, consistently building the baseline definition at the national stage, and also thinking about what kind of the building types you want to regulate. A lot of work need to be done, but that's kind of the main roadmap this group of the peoples we've been working on. Give us a little time, we will get there. Thank you.
Thank you, Bing. Ellen, are you still there? Can you hear us? Can we hear you? Just checking one more time. Ellen, are you there? Got a couple questions for you.
Yes, I'm here. Can you hear me?
Yes, awesome.
Yeah. Okay, cool.
We can hear you. Okay, so question for you, Ellen, from Sage at the Department of Energy. How do you factor in service charges?
So for the analysis we didn't include service charges. We scanned the OpenEI database based on demand charges. But in the future, we should do a more thorough analysis and include all charges.
Sounds good. And then jumping back over to Paul, question from Robert at PG&E. Could you speak more about the value energy flows as a function of time? What do you mean by this? Why is it important? And how could it impact design decisions?
Sure. Thanks for that question. Think about it in terms of if everybody, I like to think it's scale, right? If we're going to do this in very large scale, when we look at a lot of zero energy buildings, we find that a lot of them are exporting energy at some point during the day. Now let's think about that. Today, there's usually somebody else on the grid that can take up that energy. But if everybody did that, who's going to buy that energy at that moment in time? And suddenly it has very low value. We're definitely seeing some of this in California, in smaller grids like in Hawaii, where there is enough renewable energy generation that you can't turn down the traditional generation as much. And so if I add more renewables, you actually have to shed that load. And there's definitely situations where we are shedding large-scale renewables now, even though it's out there. And at that point, it has very little value, or shedding wind if you've got too much wind on the grid. And so suddenly this time dependency becomes really important. You can think of it, if everybody's using photovoltaics as a renewable generation source, that if we actually design buildings to use more energy, say between 10 and 2, and then use less energy between 4 and 8, and whether you're doing that with some kind of storage mechanism, and that could be, pre-cooling the building, pre-dehumidifying the building, putting it into ice or hot water or even batteries. If I can make that kind of shift, then I can better use that solar energy when it's available, and suddenly it has higher value again. And so that's that time dependency piece of it.
Great, thanks, Paul. And with that, we're just about out of time, so I would like to wrap it up with a quick round of gratitude and appreciation. First, thank you again to Paul, Bing, and Ellen for their great presentations. Also, I would be remiss to not plug all our other 30-plus papers that represent Panel 10. Thank you to all the authors and co-authors that we've been working with over the last several months and sticking with us through thick and thin, especially during these difficult times. Lastly, I would just like to say thanks so much to my Panel 10 co-leader, Smita Gupta, for showing me the ropes on this journey. Also, huge thanks to Summer Study Conference co-chairs Jessica and Deanna for their leadership. And finally, Rebecca and everybody at ACEEE for their tireless work and commitment. What an amazing job everyone has done to pull this conference off virtually. All right, there's another great lineup of informal sessions and social activities later today via Zoom. I mentioned one at 4:30 on zero energy buildings. Be sure to check that out. And one other one, which I'll plug, is an impromptu add-on in true summer study form, and will be a virtual guitar meetup that I will facilitate at 9 o'clock Eastern tonight. So hopefully after the kiddos are in bed, if you play guitar or any other instrument and would like to share a favorite song with the group, please join us. Or if you want to just come and listen and hang out, that is perfectly fine too. With that, I'm going to sign off. Thanks again, everybody. Take care.